This webinar is specifically designed for research scholar or those who are doing their master's thesis. So before starting this session, I will show you how we can download different data like rainfall, because in our last seminar many participants asked for it. So I will show you how we can download different types of data. So first we will see how we can download rainfall data. Let me share my screen. So is it visible, my screen?
Yes, ma'am.
Yeah. Okay, thank you.
Ma'am, can you recording this video?
Yeah, you can. So first we will see uh, graded rainfall data. So from Indian Meteorological Department, we will download the graded rainfall data. So this is, they are showing that it is high spatial resolution data, that is 0.25 into 0.25 degree, and basically like it will be by around 27 kilometer by 27 into 27 kilometer. Daily graded rainfall data set over India. Okay, and the data is arranged in 135 into 129 grid points. So what you have to do, nothing, just select the year. So let's select 2023 and just download the data. And if you are using the data in your work and if you are publishing the data, then please give citation. Okay, if you are getting any data freely, then you should give the citation in your work. So this data will be getting in net CDF file, and we will convert this net CDF into raster data. So if you have any questions in between, you can ask in the message, or you can raise your hand. Yeah, so data is downloaded. Yeah, now only you have question. Okay. Yeah, yeah,
Hello,
Sim.
good morning.
Yeah, good morning.
Can okay, so can I access the same data for Zimbabwe here in Africa, or it's just meant for India?
Sorry, I didn't get you. Can you repeat it again?
Okay, I was asking on the same
Yeah.
website. Can I ask
No. I'll show you. I'll show you how you will get international data. So this is for India.
Okay,
Okay. So Indian Meteorological Department. I will show you how we can download international data. Okay. So let me finish first. Please repeat the steps. Oh, nothing. Okay. So first you just write it graded rainfall data, IMD. Okay. And you just click this website, and then you will get this one graded rainfall data, and it is in 0.25 degree into 0.25 degree its resolution. That is, if I consider 1 kilometer equals to 1 degree equals to 111 kilometer, and then if you calculate it, it will be around 27 into 27 kilometer resolution data you will get. Okay, so then select the year and then just download it. So this data you will be getting in net CDF format, and I'll be converting this data into raster format in ArcMap. So let's take the data first. Let's download it. Then go to ArcMap, taking a new document. Then I'm bringing the data into my ArcMap. Yeah, just refresh it. Okay, so because net CDF format is not recognizable in the ArcMap, so first we will convert them. Okay, so you just in the search toolbox you just search net CDF. Okay, again I'm showing you net CDF. Search it. So here we'll get make a net CDF raster layer. Okay, click on it. Input the net CDF file. So take that net CDF file that just we have downloaded. So this one, open it. Yeah. So variable is rainfall, only one variable, X dimension, Y dimension, output raster layer by value. So everything is like they have taken it. You no need to change anything within this. So just click OK. Yeah. So the unit is in decimal degree, and yeah, so in 2003 you won't get that much variation. You can see it. So it is in millimeter rainfall, and the unit is in millimeter. And if we change the properties also, like it is very less, the variation is very less. So if we change the color variation, we won't get that much variation here. And let me classified one. Okay, stretch only it will be available. Okay, so like this way, and whatever the study area you have, you just bring the boundary of your study area, and you can clip that area, whatever the study area you are, whatever the area you are working. So you can clip that area and you will get your rainfall data. So you can see, like you can understand this thing that this is in 2023 we don't have that much variation. That's why it is coming mostly in blue, like 0. Okay. Okay. Now next we will see how we can download international rainfall data. So this is one website, like if you search CHRS data portal. When if you open it, yeah. So here we can see different categories are there. So let's first read out what it is. So the current operational, the Spartian precipitation estimation from remotely sensed information using artificial neural network system developed by the Center for Hydrometeorology and Remote Sensing at the University of California. So they have processed the remote sensing data, uses neural network function procedures to compute an estimate of rainfall rate at each 0.25 degree into 0.25 degree pixel of the infrared brightness temperature image provided by the geostationary satellites. So this resolution is same the resolution that we get for our India IMD website. Okay, and now this CCS, this is another category. So in this cloud classification system, we will be getting it in 4 kilometer into 4 kilometer. Okay, we will be getting the resolution. So we will be getting this more high resolution data from this Partian CCS, that is cloud classification system. And you will be getting this data from January 2003 to present, and hourly data, 3 hourly, 6 hourly, daily, monthly, and yearly. Okay, so now let's see how we can get it. So daily, okay, let's say I want for yearly data and domain. Okay, domain, so someone is asking for Africa data. So let's see if we can download data for Ghana. So basically here you can choose, let's see, country. So here you can choose the country if you decide country. Okay. So I'm selecting this one. You can see this is highlighted in orange color. Yeah. And here also you can choose it. So currently it is given up to 2020. Okay. I think it will be varying for from place to place. Okay, so 2020, I'm then go to download. Okay, yeah, it is 2020. Select the time format. So here we can choose different format, NetCDF, TIFF, and ArcGrid. I am choosing TIFF, zip file, and download. Yeah, so here I have to give my email ID. And download it. So just click on this link, the data will be downloaded. Okay, let's see the data, how it looks like. 1 second. Just cut it and paste it in our desired folder. Yeah, just extract the data. Yeah, now let's see. Take a new document and then refresh it. Yeah. So this is the data for 2020. So I have downloaded yearly data. Okay, let's give some color. Go to symbology and choose some color. Right. Okay. Okay. So this is all about your rainfall data. So I think it is clear now who is asking about African data, right? Okay. Now let's see. Uh, will be at that seminar, someone asked, some participant asked about evapotranspiration data. So I'll show you how you will get evapotranspiration data. For this, just go to NASA Earth data. Yeah. Now go to data, Earth data search. So here you have to log in. Like first you should register yourself in the Earth data website, and then you have to log in. As I have already registered here. So you will get here different types of data. I am searching here. So yeah, so I'll be downloading the data from Modi's satellite. Okay, Modi's. So for that, I'm just writing mode 16. Yeah. So here you will be getting your evapotranspiration data uh, uh, for each day data. Global data. You will get gap fill data. So different type of data you will be getting. And now if I choose the area, you have to choose some area, right? And so let's choose the area first. So let's choosing for this area. And data net evapotranspiration. Yeah, so now you can see it is coming in several tiles. If you want to download, you can download all. Okay, and if you want to download any single one, you can just download it. So I'm not downloading it right now. So you just click on it, and then your data will be downloaded. And here you can specify like which year data do you want. Do you want like day data, night data, or both data access? Then you should write the cloud cover also in this cloud cover. Like, so let's not mention the cloud cover currently. Short. Okay. So in this date, actually, it is not showing any data. So let's see. 24 January 1st, and okay, let's not give the So it is 2021 ongoing Earth Data Cloud, evapotranspiration and latent heat flux product. Okay. So I hope you will get an idea like how you can download the data from MODIS satellite evapotranspiration data. Okay. Temporal end date time is invalid. Okay. So you have to check the date time, like which date time do you want and what kind of data you want. You have to check that accordingly. You should search it. Okay. Now let's go back to our topic that is advanced spatial analysis. So today we will be talking about geostatistics. Okay. You know that it is in ArcMap we have one geostatistical analyst. So if we go to extension and we have one geostatistical analyst. Okay. Yeah. So uh, what does it mean geostatistics? Statistics we understand that it deals with the number. When it comes to geo, that means it deals with the earth surface or earth location. So like here we have two variables. One will be location, that is latitude, longitude, and and its attributes. Okay. So let's see how this geostatistics or basically interpolation. Why this geostatistics we are discussing, because we while interpolate any value, we need this concept of geostatistics, right? And why we need basically interpolation. So we need interpolation because if we have any point data, then that is discrete data. And if we want to make any continuous surface from this point data, so we need to interpolate it. Okay, so let's see little bit more about interpolation. So interpolation predicts values for cells in a raster from a limited number of sample data points. It can be used to predict unknown values for any geographic point data, such as elevation, rainfall, chemical concentrations. It can be anything. It can be groundwater level data. It can be water quality data. So any natural things. If we want to get a continuous surface, or if you want to see the terrain, then we need to interpolate it. Okay, interpolate means we need to estimate the value of unknown points. So here one example is given. So this is showing, the points are showing some rainfall data over this area. Okay, now you can see that only these points are there. But if I want to see the like how rainfall is distributed spatially, how what is its trend? Here we can see it is 30. It is like higher value. It is lower value. In between, it is having more low value. But if I want to see it as a continuous surface, then what we'll do? We'll go for interpolation. So if we interpolate this, we will get a raster surface. Okay, so raster is consisting of grids. And for each cell, then we will be getting value if we interpolate it. Okay, then what is the basic concept of interpolation? So the basic concept of interpolation, what is the assumption basically? So the assumption that makes interpolation a viable option is that spatially distributed objects are spatially correlated. Okay, that means that See, if we like where I am keeping my cursor at this point, at this point, I want to know the rainfall value, the rainfall value. Okay, so like if we assume, okay, how it like what it would be if we assume, so we can say that it would be like it would be varying from it could be 19, 18, 15 also, and it could be 21, 22, or it could be 26, 27. So that means as this point is close to this point and this point, so we can assume that their value will also be nearby to this 20 and 24. It cannot be 70, it cannot be 1, it cannot be generally. In general, if we think, if we assume that it cannot be like 1, it cannot be 70, so we won't get high variability in this close, in this small distance. In this small distance, we won't get that high variability. So this is the main assumption of interpolation, that close are the points, close will be their values. Okay, so here it is saying that in other words, things that are close together tend to have similar characteristics. For instance, if it is raining on one side of the street, you can predict with a high level of confidence that it is raining on the other side of the street. Correct. You would be less certain if it was raining across town, and less confident still about the state of weather in the next county. So when your distance is increasing, your assumption or your prediction about the values is also, it is less certain. It is not that much certain. You cannot say that what is happening in another county, because the distance is far. So close are the points, close will be their values. Use, Using the above analogy, it is easy to see that the values of points close to sample points are more likely to be similar than those that are farther apart. This is the basis of interpolation. Okay, so we can interpolate, elevation data. We can interpolate any concentration surface, and then we can see that how it is spatially it is distributed. Like concentration is more here, then it is going to decrease along this direction. Okay, let's get more overview. So why we need it? Why we need this interpolation? So it is saying that visiting every location in a study area to measure anything, whatever parameter you are studying, so it is not possible to take measurement of each and every point. So if we see in this case, like it is not possible to measure rainfall data at each and every location, so it will be difficult. So that's why it is usually difficult or expensive. Instead, you can measure the phenomenon at strategically dispersed sample locations, and predicted values can be assigned to all other locations. Input points can either randomly or regularly spaced, or based on a sampling scheme. So it is a different things. I'll talk about it later. Okay. So basically, interpolation tools are generally divided into deterministic and geostatistical methods. Okay. So the deterministic interpolation methods assign values to locations based on the surrounding measured values, and on specified mathematical formulas that determine the smoothness of the resulting surface. Most commonly used deterministic method is IDW, inverse distance weighting. Okay, let me know how any of one here have you used IDW? Have you used ever in Arc Map software? Whoever used, they can you can raise your hand. None of you have used till now this IDW, right? Yeah, I will tell you how to plug in geostat. Okay, so none of from you like have used this IDW, right? Okay, so let's go back. So this is the most commonly used interpolation technique. Okay, so generally what we do, because we just input, we just give our data set, and whatever the default value, we just, most commonly, I'm not saying everyone is doing that. They use just whatever the default option is there available in the software. They just click and get the result, get the interpolation surface. Okay, so this is the deterministic method, IDW. So as the name says, inverse distance weighting. So what it does basically, suppose again I want to know the value of this unknown point where I kept my cursor. So as this point 20.20 and this 24, these are nearby to this unknown point. So this interpolation algorithm, it will give more weight to this 2 points. Why? Because these are nearby, and as the distance increase, like this point, it will give less influence. So that's why it's the inverse distance weighting. If the distance increase, influence will be less. Influence of this point will be less. So whatever the mathematical formula it is using, it is designed in such a way that it works like this way. So yeah, so we have a more natural neighbor, trend and spline, but most commonly we use inverse distance weighting. And another method is the geostatistical methods based on statistical models that include autocorrelation, the statistical relationship among the measured points. So it is not just based on the distance between the points. It first see that how the data are related, how the data are correlated. That's why it is autocorrelation, how the data are correlated based on distance. And then that points will be considered to calculate the value of unknown points. You should not be on your editing mode. If you are on your editing mode, all the options will be disabled. Okay, so you should be always on the, like, disable your edit. Okay. Now see, explore data. Most basically when we go for, so here it is advanced function, and as I have said, this webinar is mostly for research students. So for research students, if like you are performing the interpolation, then you should perform it with like mostly accurate interpolation surface. You should get it. Otherwise, if you have one more option of getting, like direct option IDW here. Okay, IDW. Yeah, just you click IDW and you just click take your data, all things, and then you will get a surface. Okay, whatever the default values you are using, default values the software is giving, you can get a surface with this data. But here I'm talking about mostly accurate surface. So that's why I'll go through this geostatistical analyst tool. See, you can explore your data also. Okay, like histogram, if you see your data, so just here elevation, yeah. So your elevation data is there, like here the x-axis is representing your data set and its frequency. Okay, so it is skewed, like we can say that subject elevation is chosen, elevation transformation is none. So if you can see, like most of the data sets here having lower elevation. Okay, elevation will be low. Here you can see even, let me just follow this. Yeah, here you can see, like you can analyze your data set first. So it is a skewed data. Okay. This is the normal statistics, minimum, maximum, mean, and skewness. It is showing 0.60. That means if it is a less skewness, is you are getting less than 1, then it means that you are having long axis towards the lowest value. Okay, towards the lower values, you are having long axis of your histogram, and if the skewness is more than 1, then you are having the longest axis towards the higher values. So you should explore your data set before performing the exploration, interpolation. Okay. Okay. So let's first go for explore data, and here many options are there. We'll be talking about semi-variogram while we performing the kriging. So first we'll click on this, and then here you can say deterministic methods, inverse distance weighting, and many other methods are there. So we'll click on this inverse distance weighting, and source data set is our elevation. Data field will be elevation. Okay, and then go to next. Okay, so you can zoom it mm, to get your, yeah. So here the power, first option is power. Power means like how much influence you are giving to your nearby neighboring points. Okay. Generally the default is 2, and here on arc map we will get the option of optimization. So this option we'll be using it later. Now we'll go for this power 2. So how much power you are giving to your neighboring points. Neighbor type is standard, maximum neighbors. So maximum neighbors is they are taking as 15, and minimum is 10. Sector type one sector. So like in all directions there in this if we take 4 sectors, then it will be equally divided into 4 sectors. Your points will be divided into 4 sectors, but we are taking here as one sector. And major semi-axis. Okay. So I forgot to tell you one important thing. Basically, I will suggest you to change your coordinate system to projected coordinate system. Why? Because here we will talking about distance between the points. So whenever any linear measurements are coming, then we should change the coordinate system. Our decimal degrees is in geographic coordinate system, so it is representing an angular unit. So we should change it to projected coordinate system that represents 2D or linear unit. Your unit should be your latitude and longitude will be represented through linear unit. So for this, let's go to it. Data management tools, projections and transformations, project. Before that, we should know that our area falls in which UTM zone, right? So for that, go to tools, options, choose this universal transverse marketer, apply. Okay. So we can see here from here that our zone is falling in 45. So as we know, it is in northern hemisphere, so 45 north. Okay, so let's change it first. So go to project and take this elevation and save it. So elevation project, save it. and go to coordinate system, go to projected coordinate system, UTM, WGS 1984, Northern Hemisphere, and 45M, this one. Okay, okay, then click OK. Yeah, and the same way we will be using, we'll be converting the projection coordinate system of this boundary layer, boundary, save it, boundary output, project, save, output coordinate system, the same thing, UTM, WGS 1984, Northern Hemisphere, 45 in, okay, and okay. Yeah. So as we have changed the coordinate reference system, you should take a blank document because see till now we are our data frame coordinate system is in decimal degree. So you should take a new layer and then bring your data again. Elevation. So now our data frame coordinate reference system changed to meters and boundary output. Okay. Okay, now a geospatial analyst, geostatistical wizard, inverse distance weighting, elevation project, elevation. Yes, go to next. Just zoom in. Yeah, zoom in more or yeah. Yeah, we are see now here we are getting this in linear unit. This major semi-axis and minor semi-axis. So this is basically represent this circle. Okay, like we are saying that maximum neighbors is 15 and minimum is 10. So basically this minor and major semi-axis represent this circle. You can change it even. Let's make it, let's reduce it little bit to 5 and to 5. Yeah, you can see the changes. Okay, now let's this wait. Okay, so this red color, it is giving like this value. So uh, if we are predicting or if we are estimating the value of this unknown point, then this two nearby points will get more weights. So that is given in red color. Then this brown and then this green. Okay, let's find out where is this green. This one. So it is like far away from this point. This point, and this is this one. So here let's see the value of this point. Okay. So here we can see the value of this point. Okay. Now go to next. Yeah. So here we can see the root mean square error. It is 2.89. See, the more less value you will get, your prediction will be more accurate. So you are getting 2.89 root mean square value, and although so this is basically the predicted line or this mathematical formula. Although most of the values are falling along this line. Few points are just falling below and above this line. Okay. Now let's go back. And so just remember that we are getting root mean square error as 2.89. And now we will use this optimize power value. Okay. So power is now increased to 2.53 and then go to next. It is reduced little bit. It is 2.87. Okay. And here we will increase the radius that we have reduced. Okay. And again go to next and 2.87 it is same. See, we can optimize more and more. Okay. Okay, it is fixed to 2.87. Now finish it. So whatever the values we have given, we can get it. And one more thing is that we can export this result from here. We can like how much error at each point we are getting, we can get it. So you can export the table. Okay. You can export it as shift file or you can export it as DBS table. So I'm exporting it as shift file. Save it. Okay, and finish it. Okay, so this is our result. Okay, and one more thing we should do is that uh, okay, like we can mask the data. You can see now, like as I have not mentioned the boundary, so it is like it is going outside of this boundary, right? So what we can do here, uh, again go here, just source data set, elevation, elevation. Next, just quickly I'm doing it. I'm just taking this optimization value. Next, okay, here this option is not here. Okay, basically this here we will not get this option. Finish. I'm not finishing here. Okay. Okay. So this is inverse distance weighting prediction map, and these are the values, like red color representing the highest elevation areas, and this blue color representing lowest elevation areas. So that masking effect, like if we go through this one through spatial analyst tool, let's do this one also. Once again, Z value field will be elevation, output, raster, save it. Uh, IDW to just give me 1 second. Yeah. So output raster. So I'm not changing anything here. Just so go to the environments now. Go to the processing extent. Uh, so here in the default, you should choose same as layer boundary output. That is this layer. Okay. The processing extent, and in the raster analysis, mask boundary output. Uh, and then click OK. And yeah, Okay, it is not. Okay, yeah. So see, here we got it. Okay, and here also you have to do one more thing. Just you have to clip it. Okay, you have to clip according to the boundary. So I'm not clipping it now. Okay, now we will go for kriging. Okay, so let's before kriging, so let's go for geostatistical wizard. In the kriging is geostatistical methods. Go for kriging. Our source data set will be again elevation. Data field will be elevation. So you can see here kriging and co-kriging. So when here we have only one variable, if we are want to interpolate of more than one variable, then we'll go for co-kriging. Okay, go to next. Here we are going for ordinary kriging and prediction, and then go to next. Yeah. So this is semi-variogram we are getting now. Okay, semi-variogram. In this semi-variogram, you can see this is the distance between the points. Okay, this is the distance between the points and their values. So their values generally, this is called semi-variogram function, or through gamma we represent the semi-variogram function. And so this mathematical function defines that when the distance will increase, the value between the points will increase. Okay, and at one time it will become flat. So at this distance, after some distance, this law will not going to work. What is the law? Close are the points, close will be their values. So this is Tobler's law of geography. Okay, so after some point, this is not going to work, and this is also called here sill. Okay, here nugget is there, and this is called sill. Okay, so now this see this here we have this variogram option. Explore data, and where is variogram? Okay, yes. So it will take some time to take this elevation and take this elevation. Yes. Yeah, so here we can see it is the like the variogram, that is it is called spherical model. Okay, this spherical model is here it is increasing as a spherical function. Okay, and so like if we talk about this one, yeah. So let's see this function. You can see here all the points are falling here. Let me select once more. So what it is, basically it is this distance, you can see this distance. So the distance from whatever the 2000 points are there, here it is. So distance between each points are measured first, and then they are sequentially they have given here. So 0 to 0.15. So all of the points you can see. Again, if I see this, if we look about this bean, so it will take some time basically to load the data because many points are there. So you can think about it. If you like, if I give you this task of calculating the distance between these 2000 points, okay, so this is like the distance, that is zero point 0.5 to 0.29. So again, all the points, because here we consider all the points. In IDW, only nearby points are considered, but in kriging, first the algorithm see that how the values are varying based on the distance between the points. Okay, and as we say that if the distance between the points increase, the value between them will also going to increase. And this law will be followed up to some distance. This distance is called sill. So this is will be followed up to some distance, and then it will be flat. Then this law will not be applied. Okay, and this is number of lags means this one. So number of lags are here 10. You can even increase it. You can increase the lag. Okay,